Hey everyone, welcome back to another video from 197 Concepts. So in this video, I will be telling you how to establish a serial communication and how to use the special function registers that are related with the serial communication, of course using with 8051 microcontroller. See, in the last videos, during the timers video, I've told you that there will be some cases where you need to communicate some devices outside the 8051. So in those devices, one of the uh, case is establishing a connection for a data exchange. So let us say I'm having processor 1 and not processor 1, microcontroller 1 and microcontroller 2, and I need to establish a communication between these two devices. Now you might think that for communication we can use analog to digital converters and digital to analog converters. So those are just the converters. They cannot establish a communication between the two microcontrollers by using those two devices, that is ADC and DAC. Those are used to convert signal from one form to another form. What I am talking here is I'm talking about the information exchange between two microcontrollers. This is possible only through the serial communication. Okay, so for that purpose, the 8051 comes with built-in serial communication, and the registers that are used for serial communications are S buffer, that is serial buffer, and SCON, which is serial communication. Okay, so before going into the experiment, before going to establish a connection or a communication, let us know what is this SCON and SBUF. And one more thing you have to know is you have to know what is baud rate. Of course, you will be familiar with serial communication. You have to know what is SBUF, SCON, and what is baud rate. And yeah, these serial communications are controlled via the timers itself. So that's the thing I believe you have to know. Let us start the video. So the very first thing that you have to know is what is SBUF. You have to know. Let me change the color. So you have to know what is SBUF and what is SCON. So this is S stands for serial and buff stands for buffer. Now you might be familiar with buffer. So buffer is nothing but it is a temporary storage register. That's it. So I'm having two separate blocks and I want to transfer data from this block to this block, but this block is busy for time being. It cannot store the data or it cannot accept the data that is sent from first block. Okay, so second block is busy and it cannot accept the data that is sent from the first block. So what we do is instead of directly sending this in this manner, what we do is we pass it through a separate register. Okay, so this is a register and then we give it to the block 2 or module 2. So this particular register is nothing but your buffer register. So it does not manipulates the data, it does not changes the data, it does not do any operation on the data. It just holds the data for some short duration. It's temporary. Okay, so that's the main thing. And the buffer, it is used for that main purpose. So there is nothing new that you have to study about SBUF. It is just a temporary storage device. All the magic happens at SCON. Okay, na? So this SCON, which is configurable, configurable. Okay, so that is serial configurable register. Okay, this is an 8 bit addressable register. So total of a total there are 8 bits: 7, 6, 5, 4, 3, 2, 1, 0. So total of 8 bits, and all 8 bits are individually accessible. So I can individually access the 0th bit, I can access the first bit, second bit, third bit, fourth bit, fifth bit, sixth bit, and seventh bit. All the 8 bits can be individually accessed. So there is no problem. You can access them as a group as an 8 bit. Along with that, you can access them individually. Okay, now what are these 8 bits? So definitely each bit has their own purpose. So those 8 bits I have searched here. Let me just write those: SM0, SM1, SM2, REN, TB8, the RB8, RI, and TI. Okay, so let me write here. Okay, I will go from here. SM0, SM1. So this is RI, this is TI, RB8, TB8. Let me just check it. SM2, SM2. So I'm writing it down. So REN, this is, uh, yeah, TB8, RB8. So these are the 8 bits. So just let's speak about them. Let's talk about them briefly. Okay, now. So first one is SM0, then next SM1, then SM2, then next TB8, RB8. Yeah, there's a S enable, right? S, is it not S enable? It's just R enable. REN, then TB8, RB8, TI, R I. Okay, so these are the 8 registers. So this one is 0, 1, 2, 3, 4, 5, 6, and 7. Yeah, I will change the color now. Right. So RI is nothing but receive interrupt. Okay, so this particular bit will be activated when there is a problem in the receiver. Okay, when you have some problem in the reception section of the 8051. Similarly, when there's a problem for the 8051 to transmit the data, then particular pin, that is TI, which is called as the transmit interrupt, will be activated. So these pins will inform that there is a problem for transmitting data and for receiving data to the arithmetic and logical unit of the 8051. Now RB8 and TB8. So wherever you see R, that's receive, and T is transmit. So this is also receive. Okay. So RB8 means, see, keep in mind that when you're doing serial communication, your data will be sent in a packet manner. It is not sent just like randomly. Okay, so 8 bits which you are sending uh, will be packed as one set, and then so here you will be having 0 to 7 bits, and then at the starting bit you have a start bit. Okay, that tells from here on your data is going to start, and then finally you will have a stop bit. Okay, so this in this frame, your data will be sent. So this is your data, and this to this data, a start bit and a stop bit is attached. So that's what this RB8 tells. Okay, RB8 tells that I have received the 8 bit. You can stop the reception from the other device. Similarly, TB8 tells that I have transmitted the 8 bit. There is no need to transfer any data more. So this is received 8th bit in the packet. Okay, so this is transmitted 8th bit in the packet. Okay, to get a much better understanding, just Google it. You will get you will get a clear idea what I'm saying here. Okay, and then 4th bit. This is RE enable. Okay, not RE enable. This is receive enable. When this particular pin is logic 1, when this particular pin is logic 1, then only the 8051 is able to receive the data from the other device or other microcontroller. Otherwise, it won't be able to. It will be just transmitting the data. It won't receive any data from the other devices. Now, this is SM2 is nothing but this is a mode selection pin. Okay, mode selection pin. Generally, we don't use it. Mode selection bit. Okay, even these two, sixth and seventh, these two are the mode selection bit. So this is the zeroth bit and this is the first bit. We are going to use only these two bits, as we are having four different modes for initializing the 8051 in the serial communication. So those are 00, 01, 10, and 11. Again, just like timers, mode 0, mode 1, mode 2, mode 3. So what's the difference between all these three modes? You can see here in the website. Okay, let me just take open this one. Yeah, is it visible if I use yellow? No. Yeah. See, so mode 0, mode 1. So there will be four modes just mentioned here: 00, 01, 10, and 11. So the difference is the type of clock frequency you're going to take, and based on the clock frequency your baud rate will be different. So in mode 0 you will be having 1 by 12th of oscillator frequency. For example, my oscillator frequency is 12 megahertz. In that case, when I'm starting the serial communication in the 8051 in mode 0, then I will be having 1 by 12th of 12 megahertz. Okay, so I will be getting 1 by 12th of 12 megahertz, which is equals to 1 megahertz of frequency. So at 1 megahertz, I will be doing my serial communication. When you go for, I will speak about mode 1 later. When you go for mode 0, you will be getting 1 by 32 times of 12 megahertz. Okay, so this one gets cancelled. And how many times does it goes? Yeah, whatsoever. I'm not good at that. So if you cancel that, and you get some value. So that's the value at which your baud rate is going to work, not the clock frequency, not the communication frequency. That's the baud rate you're going to work at. Whereas when you go for mode 3, you're going to use a determined baud rate using timer 1. Okay, and you might have observed here there is no specific bits for mode 0, but when you come for mode 1, mode 2, and mode 3, you are having 9 bit, 9 bit, and 8 bit. Okay, so that's the difference what you are doing between zero mode, mode 1, mode 2, and mode 3. But by default we are going to use only mode 1. uh, this in mode 1, here in mode 1 you are going to send 8 bits of data at one particular time using timer 1 with your specific baud rate. Okay, and yeah, baud rate, there are three types of baud rates that are commonly used. Those are 9600, okay, then next 4800, and then 2400. So these three are the baud rates that we are going to use in our serial communication for 8051 itself. So these are low speed baud rates, okay. When you go for today's technology, it's somewhere between 1 lakh 11,000, so on. Okay, it's way above the 9600. So these are used for low speed communication itself. So let us stick to these baud rates. It's a better understanding, and these are the basic baud rates. And for initializing these baud rates, I'm going to use mode 1. Now you might ask me, what is the meaning of baud rate? Let me just clear it once. Let's go back to bamboo paper. Okay. So now you are familiar with the SCON register, and now the next thing that you have to know is what is the meaning of baud rate. Okay, So baud rate tells us how many times your signal is going to change in 1 second or in one set duration of time. So now let us take an example. For example, now I'm having a signal just like this, a clock pulse with logic 0 and logic 1. So let us say this is one complete machine cycle. So if I'm talking about timers, let us consider that these two pulses equals to one clock cycle. Now within this one clock cycle, one clock cycle, one machine cycle. So the logic here is 0, 1, 0, 1, and then 0. Okay, when you come here in at this example, so if you see the number of times the signal has changes, first it was 0, so this is the first time change, this is second time change, third time change, and fourth time change. Okay, if we neglect this value, so if we even count this value, so a total of 5 times the signal has changed its state. It can be either from logic 0 to logic 1, or it can be from logic 1 to logic 0. I'm not talking about specific transition. I'm just telling how many times the signal has changed. This number of times the signal has changed is tells the baud rate. Okay, did you get the point? So the number of times the signal has changed is nothing but your baud rate. Now, when I'm saying 9600, this tells me that my signal, my communication signal is going to change 96,600 times per second. For 1 second, my signal is going to change 600 times. Okay. Similarly, when I'm speaking about 4800, that tells me that my signal is going to change 4800 times. So it's going to what we say? It's going to change its state from logic 0 to logic 1, then logic 0, then logic 1, then logic 0, like that for 4800 times per second. Okay, so that's the baud rate. And similarly, what we have 2400. So this might seem a huge value for timing, but believe me, this is the least amount of baud rate that we are getting now. There are some situations where we use 2400 and below 2400 also. So there are such conditions also in the previous days. So in today's world, the basic is 9600, and next is I think 11,200, double of this. So this 600 will give you 2,200, and 9,000 will give you 18,000. So 18,000, not 18,000, 19,200. Okay, so the next baud rate is this one. So for our experiment purpose, we are going to check 2400, 4800, and 9600. These three baud rates. Then the interesting fact here is, in order to establish this baud rate, you have to go back to timers. Okay, so again, you have to know the basic timer calculations, that is the timer frequency, and then timer tick period, and then what we call counts. Okay, uh, counts, and then preload value. So these are the things. So if you want to know what these are, I will share a link in the description box. Have explained these in detail in another video. Just go and check that out. So these are used for calculating timers. So what should be the preload value and how much delay a timer will be able to give is dependent on this four parameters. What for serial communication, for serial communication, we are having some different parameters. So timer frequency is the same. This is nothing but f oscillator divided by 12 megahertz. Okay, so that is standard. Then after this, you have another formula, which is the divider formula. Divider formula is equals to timer frequency divided by 32 multiplied by baud rate. Baud rate. Okay, so this baud rate is your required baud rate. It can be 9600. If we are talking about our experiment, this is the required baud rate. Okay, if you're talking about our experiment, it can be 9600, it can be 2400, or it can be uh, 4800. So we will try all these three and I will show you the theoretical calculations also. Then finally, what I have to do is load a I have to load a value into the timer, which is again called the preload value, which is equals to uh, 256 minus divider. Now, in the timers, you might have observed preload value equals to preload value equals to maximum value subtracted by count. Here I have defined a value. The maximum value is always 256 because here we are using one, timer one, that too in mode 3. So this mode 3 is nothing but your 8-bit. Yeah, sorry, I've mentioned the number incorrectly. It's mode 2. So 8-bit auto reload mode, because I don't want my communication to carry on for one specific period of time and stop there itself. I want my serial communication to go on, to continue itself even after completion of the timer. So even if you want to continue your serial communication even after completing the specific duration, no such case is there. For that particular thing, what you have to do is you have to again restart the timer. Instead of finish again restarting the timer, what I'm doing is I'm auto reloading the timer with the same value. In that way, I can carry on my communication continuously without breaking it. Okay, now, so that's why in 8-bit mode, the maximum value that I will be having is 2 power 8, which is nothing but 256. So that's why I've written here 256 minus divider, this one. Okay, so let us try once. So for your easy understanding, what I'm doing is I'm taking timer frequency equals to f oscillator divided by 12, and this I'm assuming it to be 12 megahertz. Okay, 12 megahertz divided by 12 will give me 1 megahertz of value. Okay, then next what I'm going to do is divider value. So divider equals timer frequency divided by 32 into required baud rate, RBR, which is nothing but which equals to 1 into 10 to the power of 6 divided by 32. Now if I'm going with 9600, the required baud rate will be 9600. So if I solve this, that will be 1 into 10 to the power of 6 minus 2 divided by 32 into 92, right? So the 100, the 9600, I'm writing it as 96 into 100, and that 100 goes up. It will be 10 power 6 into 10 to the power of minus 2. So finally, that will be 10 to the power of 6 minus 2. Now I have to multiply 32 into 92. So let me just open the calculator. So 32 multiplied by 92. The value is 2944. So which is equals to 10 to the power of 4 divided by 2944. Again, 1 divided by 2944 will give me some exponential value, right? Multiplied by 10. This is scientific, yeah. 10 to the power of 4. So that's 3.3967. So that's 3.3967. Now, when you go for the preload value, since it is having only two values, that is logic 0 and logic 1, you cannot represent the decimal values. So this one will be rounded up to 3. So 3 is the final divided value. Now, the preload. preload will be 256 minus divider, which is 256 minus 3. This is 253. Now observe here. So all the 8 bits I'm going to write. I'm going to start from 1, 2, 4, 8, 16, 32, 64, 128. Now by adding these bits, I have to get 253. So definitely I need 128 and I need 64. So let's just do a rough calculation here. If we observe here, I will change this to a regular one, standard one for better visibility. 128 plus 64 plus 32 plus 16. So a total I will get 240. So definitely it's below 253. I'm going to put all logic ones there. Then next, sorry, not this one. Then next, plus 8 plus 4 plus 2. So up to here I'm getting 252. I need only one. That's why I'm going to cancel this value and I'm going to add only one, which will give me 253. So that's why it's 1101. If you combine these 4 bits, this will give me a value of F in hexadecimal, and if you combine these 4 values, you will get a value of D. That means the preload value, if you convert 253 in hexadecimal, your value that you have to load in timer is FD. Okay, done. Now this value has to be loaded into the timer. You have a clarity of that. Next, you have to establish or you have to configure the serial communication registers. For that, the serial communication register, the scon, must be loaded with the value 50h. Now why is that? When you convert this into binary form, so 5 will be written as 1010 and 0 will be 0000. Now if you observe this, oh, sorry, I've written it wrong. So it's actually 0101 and 0000. Okay. So if you observe this, this is the receive interrupt, this is the transmit interrupt, this is TB8, this is sorry, RB8, TB8. Okay. So these 4 bits are not of our use. These 4 bits are not of our use for the time being. What we need is these first 2 bits, which is SM0 and SM1 and the SM2 and the receiver bit. This bit. Okay, so 01 tells us that we are going to initialize our serial communication in mode 1. Now, what is mode 1? You can see here. So, mode 1 is nothing but 8-bit UART with the timer 1 determined baud rate. Okay, so that's why I'm going to initialize SCON with 50. And then in this bit, this particular bit, you are going to put logic 1. So this bit, when the fourth bit is, especially the fourth bit is logic 1, only then you can get a reverse communication. So you can get a communication from a device, or else you can say that the microcontroller can receive the information from the device outside itself. Okay, so it can get a reverse signal, otherwise it won't be able to read the data or it won't be able to read the information. So that's the main purpose. I have to initialize my scon with 50h. Okay, so that's the whole thing. Now if you shift to the program, this is the program. Okay, so yeah, let me just delete this. Now, if you come to the program, so this is just originating with 0h, and then I'm taking a long term towards the start in order to skip this particular thing. This ORG0030h is used only for interrupt vectors. So, for receive interrupt or tap interrupt and all, this particular register is going to be used. So that's why I'm just going to jump from here. I'm going to skip this line and come towards this start. Okay. So at the start, what I'm going to do, I'm going to first of all, I have to use timer 1. So timer 1, for that I have to initialize T mode. So this is the value hash 0 to h 0 sorry hash 20h. Search for the T mod and you will get a clarity why I have initialized this particular thing. Okay, so why I have loaded this value. Again, it's the same thing. It's 0010 and then 0000. If you observe this particular bit, this one will tell us that this is timer 1 control, this is timer 2 control of T mod. Oh, sorry, timer 0 control of T mod. So this one will tell last two bits. So even here also, I have written only three zeros. So these two last two bits will tell us in which mode you are going to initialize your particular timer. So timer 0 or timer 1. Just search for T mod, you will get a clear idea. Now, I have to load timer with 96 baud rate. Okay, so in order to get a 9600 baud rate, I have to load my timer one with FD value. The reason is here. Yeah, I'm not able to change because of this thing, because of this. Okay, so preload value. So in order to get 253, so if for three transitions. So 253, 254, 254, 255, and 256, your signal is going to change 9600 pads. Okay, so that's why I have to load my timer with FDH. Then I'm going to initialize SCON register with 50H. And then finally I'm going to set the run bit of timer one. And finally I'm going to transmit a signal. I'm going to transmit the data. This cannot be directly transmitted. It have to move. It has to be moved towards the accumulator. See, whenever you're giving an hash, it is an immediate data, and if you give a number like 3, this is the immediate information that you're going to work on. But if you give two quotations and 3, this number 3 is no more a number, it is a character. Okay, so in this form you can do 3 plus 1, but when you keep quotations, this 3 plus 1 is no more applicable. It will just say that there is some error in the uh, data type. So that's why, so since I'm going to transfer a character, I have to keep it in a quotations. Then I'm going to call the transmit subcall, and then finally after coming out from there, I'm going to loop this only this main section. Okay, so this all I don't need to initialize again and again. I just need to initialize it once. I have to just run this multiple times so my data keeps on transferring. Then when you come to the transmit section, so first move sbuf comma a. This tells that the as the comment here, you can see here the character a has to be loaded into the serial buffer in order to transmit. Then finally I have to run the timer. So now jump if TI is not set. So TI is transmit interrupt. Okay, this is familiar. This you have seen in SCON register. So until this is logic one, you keep on jumping from this line to back to the label. Okay, so until your TI is 0, it is not set, you have to keep on jumping from wait to back to that label. Once TI trap interrupt is set, that means TI equals to 1, then just don't jump, clear TI and return to the main program. Then again you have to repeat it in the same manner. Okay, so that's the whole program. And if we just run it simply, okay, I've already typed it here. So in the keel processor, in the keel software, one thing that you have to observe is go right click on the target, options for target, and the output. I have done the calculations for 12 megahertz, so the frequency must be here 12 megahertz. So let us try here, click on OK, then check it once. So no syntax errors, just debug, start and stop debug session. Okay, and when you come here, okay, yeah, that's the problem. So when you come for serial communication, you have to be exact with the frequency values. So you cannot round it up to 12 megahertz. You have to definitely round it. You have to keep it exact. Okay. So that's the main mistake. I think I've done it. So instead of that, 11.0592 megahertz has to, this has to be accurate. Be careful of this. By default, it will be 12 megahertz when you start a new project. So by default, it will be not 12, 24 megahertz. Just erase that value and type this one 11.0592. Click on OK, build the target, debug, start and stop debug session. Okay. Now let me see. I believe there won't be any errors. Yeah. Now there are no errors. Now, if you run this, if you press function key F5, or yeah, wait a minute. I believe this is running. So in order to check the output, you need a serial monitor. Where is the serial monitor? Serial window. Yeah, see here. I will take this out. Okay, see this. You're continuously getting a character and all. Okay, you're going to get a continuous character. If I close this, stop it, and stop the debug session. Let me do it once again. Okay, so I've closed the debug session. Again, I'm going to start it. Okay, now let us take the serial window beforehand. This is the memory. There is a C watch 2, register windows, memory 1, serial window. Yeah, UART 1. Okay. Now here, when I run this, automatically you're going to get the print of character A, and all in 9600 baud rate. Okay, now. So now this is one way of checking. The another way is you can simply check this same output in the Proteus software also. So I'm going to just open my Proteus software. Proteus software, and here I'm going to create a new project. It's not responding. Yeah, new project. Uh, I will just store it on the desktop. Desktop, select folder. I will create one. Just a minute. On the desktop, new folder. It's serial communication. Okay. Enter. Select this one. Select folder, and then here I'm going to type serial communication because I'm planning to show you all the three baud rates in this same thing. Click on enter, next, 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 finish. Okay, I'm trying to show you all the three baud rates only one circuit diagram, and place 8051 microcontroller. Yeah, you won't be having 8051, you will be having 89C51. So this is 8051 based microcontroller. Click on OK, right click it and place it. Okay. If you observe here, by default, you will be having transmit and receiving pins. So by using these two pins, we will try to get our character. Okay. Just go on this virtual instruments mode, and I need a virtual terminal. Right click, place it there. Now the connections part. Just do the opposite connection. So this receiver should not go to receiver, it should go to the transmitter, and this transmitter should go to the receiver. Okay. Now if you double click on this, you have already a baud rate of 9600, and this is definitely then generating a baud rate of 9600. So no problem. The next main thing is you have to dump the hexadecimal file. In order to dump the hexadecimal file, first of all, you have to create it. Stop the debug section session in Keel, come back to your main program, right click on target, options, and output. So I've already checked this. That's why I'm getting here create hexadecimal, create hex file. If it will be like this in this panel, click OK. Okay. So initially, if you build target, there is no such creating hex file. So for that, for creating the hex file, you have to go for target, options for target, output, check this box and click on OK. And then again, build a target. So now you will get the line creating hex file. Okay. So this will be stored in objects 9600. Now just come back to your Proteus, double click on this program file. If you see this tab, you have to click on the browse, and that is I've stored in a very deep location. Just go where you have stored the project. Okay, so now I've stored in a very deep location, so I'm just going to open it. Yeah, it's college subjects DCP MPMC experiments. So SCON 9600 objects, and this is the hex file that I have to dump it into the 8051 controller. So just click on that and click open, OK, and then simply run the file. So you will get the character. Yeah, you're not getting the character. That's because I hope it's just this 11.0592 megahertz. Let me check it now. Yeah. So you can observe here that's a small difference, and because of that you are not getting your character. So here you are getting you can say that you are able to transmit the character A into the serial terminal, at the same time you are able to receive it. That's for 9600 baud rate. In order to get a serial communication in 2400 baud rate or 4800 baud rate, let's go for 4800 baud rate. What you have to do is you have to just do these calculations again. So the timer frequency again, it will be uh, f oscillator divided by 12, which is equals to 12 megahertz divided by 12. Again it will be 1 megahertz. Okay, it is definitely 1 megahertz. Now the divider will be f oscillator divided by 32 into required baud rate. So this will be 1 mega divided by 32 into 4800. So this is 1 into 10 to the power of 6 divided by 32 into 48 into 100. Open the calculator. So 32 into 48 will give you 1536. So this is equals to 1 into 10 to the power of 4 divided by 1536. Yeah, 1 divided by 1536 will give a value of some exponential value. Now I have to go again back to scientific, and this has to be multiplied. Sorry, 1 divided by 1536 multiplied by 10 to the power of, okay, that's exponential, it's going to take 0. So instead of that, let's go in the standard mode. No, there is no exponential, so I have to go for scientific. Okay, so directly 10, oh no, that's the wrong one. So 10 to the power of 4 will give me 10,000 divided by 1536. That's 6.510. Okay, so 6.510. So 6.510. So since there is no 6.510, it can be approximated to 7. That's why the preload value will be 256 minus 7. So this will give a value of 249, I believe. So 256 minus 7, 249. Now this 249 has to be converted into what we say hexadecimal. We can do it right here. So just let me write all the bits once. 128, 64, 32, 16, 8, 4, 2, 1. So for 128 plus 64 plus 32 plus 16 will give a total of 240, right? I just need 9 plus 8 plus 0 plus 0 plus 1 will give 249. That's why it's 11111001. So if I write it quickly, 11111001. These 4 bits will be F and 8 plus 1 will be 9. Now if you check this value for a baud rate of 98, 4800, you have to get the value of FA. So we did the mistake somewhere. Okay, he might have taken only 6 instead of 7. Yeah, if you go for 11.0592, it will be 6.4 and it will be rounded up to 6. So that's why you have to load with the value of FA. Okay, so this is the theoretical calculation that you have to do, and for your reference, you are going to get the values right here. Okay, so I'm going to load with FA. Where is my key? So FA instead of FD in timer 1, I'm going to just keep it as FA. All the other program is same. Just create an hex file. So no errors. Debug. Start and stop debug session. Okay. Before running the program, open the serial communication window. That's the memory window. UART1. Okay. Now I have to transmit character A. Okay, let's do this way. Instead of transferring character A, let us change the character. Like say P. Okay. Create the hex file. Debug. Start and stop debug session. Okay. Now here, if you start this, see, you're getting B is getting transferred. So this is okay. Now if you stop the debug session, and by building the target, since I've already checked that create hex file checkbox, so I've already created a hex file, and this hex file is already loaded into this. Okay, so now when I run this, I will get some other character. I will just pause it for 1 minute. See, I'm not getting the character properly. This is because you have initialized the baud rate as 48, but you are working here with 9600. So your baud rate has to be changed to 4800. Click on OK or press enter, and then you run it. See, now you are getting the characters properly. Okay, so this is establishing serial communication with the baud rate of 4800. And finally, for establishing a serial communication with the baud rate of 2400, what you have to do is just go for the key program. Is the same thing. Instead of FA0, what you have to load here is F4. Okay, so F4. So if you want, let us do the theoretical calculations once with 11.596, 0592. So equals to F oscillator is 11.0592 into 10 to the power of 6 divided by 12. So it's not possible for me to enter those values. So I'm going to take a mobile. Okay. Here, it is clear. Right, 11.0592, not multiplied by, divided by 12 will give a value of 0.9261, will give a value of 0.9261 into 10 to the power of 6. Let us keep that megahertz similar in the init panel. I don't want to multiply it. So now divider will become uh, Timer frequency, which is 0.9261 multiplied by 10 to the power of 6 divided by 32 into required baud rate is 2400. So this is 0.9261 divided by 32 into 24 multiplied by 10 to the power of 6 divided by 10 square, because that is 100. Now this will give a simplified value. So first of all, 0.9261, 0.9261, keep it that way. First of all, multiply 32 into 24. That will give us 768 value. 768. So into 10 to the power of 6 minus 2. That will give 4. Now this, so 0.9261 divided by 768. It is 0.001205 multiplied by 10 to the power of 4. Now you have, this has to go 4 decimals. So 1, 2, 3, 4. Okay. So 12.058, which is approximately 12. Now the preload equals to 256 minus 12. This is nothing but 6 minus 2 is 4, 5 minus 1 is 4. So 244. Now 244 has to be converted into hexadecimal. So again 128, 64, 32, 16, 8, 4, 2, 1. So again, this can be shown in the calculator itself. So 128 plus 64 plus 32 plus 16 will give a total of 240. Now I need only 4. So that's why what I'm going to do is 0 plus 4 plus 0 plus 0. Okay, I have given their 5 values. So these all will come 1, and this is 0100. So I'm going to write that 1111 0100. This is F and this is 4. Now see, if you have taken 11.0592, you have got the correct value. And if you check that, it is F4. Okay, so it was just the matter of frequency. I have taken it for 12 megahertz in the second case, but you have to actually go for 11.0592. In the case of timers, the frequency can be rounded up to 12 megahertz, but for serial communication, to establish it, you have to go with the accurate values, 11.0592. Okay, now if you come here, where is the key? Yeah, if you come here, you just have to change that. So yeah, I will change the character as C. Okay, debug, start and stop debug session. Okay, and yeah, I have already got the URT and run this. Okay, I have not built the target. That's why it's just showing me the previous value. So now I will build the target. I'm at the same time I am also building the hexadecimal file. Now start and stop debug session. Okay. Now if you run this, see, you're getting a character of C. To verify this in Proteus, just open Proteus. If you run this, you will get some other character because you have initialized for 2400. That's why double click on virtual terminal and change the baud rate to 2400. Click on enter, and then you will get the correct values. Okay, so that's for the experiment. I think, I hope you have understood the difference between baud rate, the different baud rates, 2400, 4800, and the 9600, and the way that you use to establish a serial communication between these three baud rates. Thank you.